In this video, we're going to discuss the concept of half circuits and how they can be used to simplify analysis of full differential pair amplifiers. So here on the left we have a MOSFET differential pair example circuit where we have perfectly matched drain resistors and perfectly matched MOSFETs Q1 and Q2. So as long as our differential input voltage is applied in a complementary balanced manner, and that is to say that it will be plus VID over 2 on one side and minus VID over 2 at the other gate terminal, then that leads, as we've shown in the lectures and previous videos, to a virtual ground state at the source. This allows us to simplify the circuit based on our symmetry. So our full differential circuit on the left can be analyzed using just the small, much simpler circuit on the right hand side. So you can see that we still have our RD resistor, in this case going to ground, and we have one of our inputs, VID over 2, going to the gate terminal, whereas in this case our source goes straight to ground, and that's because of the virtual ground that we formed by the circuit symmetry and the balanced input with the plus and minus VID over 2. So this circuit is only valid for the differential input case. Now what about a slightly more complex circuit? And this is the reason we might be interested in half circuits. If we're given this circuit to analyze, then that can be quite complex. So we want to simplify it as much as possible. So in this case, the half circuit will become that shown on the right here. So as before, we still have our drain resistor, but instead of our source going directly to ground, we now go via the source resistance RS. But due to the symmetry of the circuit, between our RS resistors we still have a ground, a virtual ground. So after our RS resistor, we then have the ground terminal. Another interesting point of this conversion is you can note that the load resistor is now RL divided by 2. And that's simply because the load resistor in the original circuit crosses the line of symmetry of the circuit. So our circuit is symmetrical across here, and therefore within one half circuit we would only have half of that resistance seen. And so of course this circuit here could also be redrawn as two load resistors, each being RL over 2. And then it's clear how the symmetry is applied in order to get to the half circuit on the right. So the half circuits can also be applied to the BJT differential pair. In this case, we have a very similar approach to the MOSFET differential pair. We still have our collector resistor in the new half circuit, and our emitter terminal can go directly to ground thanks to the virtual ground setup in our full circuit on the left. And finally, we'll take a look at the common mode half circuit. So if we're interested in our common mode response, so here we have our primary common mode voltage along with an incremental common mode voltage, and we're interested in knowing how the circuit output will respond to that, we can again use a half circuit analysis because we still have symmetry across our circuit. So in this case, the first step would be to switch our circuit to a small signal model. So here we have removed the current source and set the power supplies to ground. This immediately simplifies our analysis, and this is the state set up by our large signal VCM. So now we can take a look at how this circuit converts into our two half circuits on the right side. So as with before, there's no change in the output drain resistance, but we can see that of course we no longer have a virtual ground condition at the source terminals, and therefore our half circuit includes the resistor RSS before going to ground. It's important to note here that in the half circuit the resistance is actually 2 RSS. So this is due to the fact that in our original circuit we have a current source I, which was shown to have the resistor RSS in parallel. Now, as our line of symmetry intersects our current source I, this resistor in its current configuration would break the symmetry between our two half circuits. So that can be redrawn in a more symmetrical manner. Where each of these resistors is equal to 2 RSS. So of course the total resistance remains the same as the original circuit, but we now have perfect symmetry.